Oops! As much as we try to avoid them, accidents happen. Some get away with slight grace, while some are not that lucky. However, it is the job of an automotive company to provide the occupants of their vehicle with the best protection they can. A car's safety is mainly dependent on its chassis. But what exactly is chassis? Before dwelling into the details, let me introduce myself. I am Karthikeyan Varadarajan, Senior Vice President working for EDS Technologies, largest solution service provider in India. I come with 10 years of experience from automotive industry, and last 2.5 decades I have been with EDS Technologies and serving many customers in the space of automotive, aerospace and white goods. A chassis is the load-bearing structure of the vehicle. If I have to compare it with a living thing, I would say it is very similar to the human skeleton. It is a structure that gives an automotive shape and the strength it needs to stand up. Every type of the vehicle requires a chassis, whether it is humble bicycle or a mighty truck. Just as human bodies come in different shapes and sizes, so do the chassis. They vary according to the function and vehicle they are used to. Automobile companies use different types of chassis. It is the oldest design of a car chassis. Early manufacturers were using the chassis design because it eases the manufacturing process. It is still used to build towing vehicles as the weight of the chassis helps pull other loads easily. Since the chassis design looks like a ladder, that is why it is called ladder frame chassis. The lack of a crumble zone and a weak torsional rigidity results in bad cornering. Thus, the ladder chassis is not more widely used. This design is mostly used in race car because of the safety it provides. It is a very complex design which makes automating the production process very difficult. Moreover, it takes up more space which results in less space for occupants. Monocoque in French means a single shell. It is called a single shell because of both the chassis and the frame are built together as one. It is safer than the other chassis designs because of its gauge-like structure. The chassis increases the ride dynamics because of the center of gravity for this design is very low. It allows manufacturers to make more agile, aerodynamic automotive models. These chassis are designed to hold the car together and provide safety for the people inside them. Each has a unique design depending on the level of risk and the impact it must withstand. But how do we measure the safety factors of these structures? The safety of the car is quantified by something called crashworthiness. Crashworthiness connotes a measure of the vehicle structure ability to plastically deform and yet maintain sufficient survival space for its occupants in crashes involving reasonable deceleration loads. In other words, crashworthiness refers to the ability of the car structure to deform in a crash but still maintain enough space preventing the occupants from being crushed. A car structure must undergo progressive crush folds to absorb the kinetic energy of the crash, must be able to control the crash deceleration pulse and have a properly designed frames to structure the minimize intrusion of the occupant's cabin. But who decides if a car is crashworthy or not? In India, ARAI, Automotive Research Association of India, provides both the testing facility and certification. Although there are many providers of infrastructure and standardized certificates, in the recent years, the NCAP or New Car Assessment Program by Towards Zero organization has become the standard in automotive sector. They even push the Indian manufacturers to produce safer cars under the Safer Cars for India campaign. Crash tests are mandatory, but building a physical model for every crash test scenario is very expensive and time consuming. This is where the concept of virtual prototyping comes into picture, where FEA, popularly known as finite element analysis, is the basic building block. It allows you to design virtual prototypes and simulate these crash test scenarios, thereby reducing the number of expensive physical tests. The Tata Nexon scored 5 stars for occupant safety and 3 stars for child safety in the NCAP test. It is considered as one of the safest cars to buy in the Indian market. Nexon weighs around 1300 kg to 1400 kg. When it hits a hard barrier at 64 kilometers per hour, then the force generated there will be around 3000 Newton, which is equivalent to a huge fist of a professional boxer knocking the living daylights out of you. But the frame's design should be such that it absorbs most of the force, preventing the occupant from taking the fatal hit. Now, designing such a frame needs a lot of iterative testing. So, naturally, we have to simulate this scenario in a finite element software. Let's take a look at how an FEA software simulates the real scenario. Well, they use simple principle, Newton's third law. The law of conservation of momentum states that the force applied by an object A on an object B, the object B exerts back an equal force in magnitude, but in the opposite direction. Simply put, every action has an equal and opposite reaction. In other language, namely maths, it is the initial momentum is equal to the final momentum. When a car hits a barrier, it exerts the same amount of force on the car such that the car decelerates rapidly and the momentum reaches 0. Because the barrier cancels out the car's momentum, the car is deformed. FEA software calculates the force exerted on the car by the barrier, simulating the crash scenario and damage to the structure. Engineers simulate hundreds of such crashes. They process the data, define the problem, implement the change, and test the design again and again. This process is repeated until the design matches the desired load-bearing requirements. There are multiple software we can use to simulate crash tests like LS-DYNA, Abacus, PAM-Crash, Radios, and Madimo. But before we venture into crash tests, we need a design in place. As a first step, a very simple model is analyzed with simple elements with the static acceleration loads and to obtain an impact chart at key point locations in the chassis. The results from these analyses provide very important insight into the chassis behavior before the entire 3D model is built. Impact analysis is then performed over the entire relevant FEM model using an explicit dynamic solvers, mostly Abacus, LS-DYNA, and PAM-Crash. The designers then work on designing the body in white of the car. The BIW translates to body in white, which is the frame and the skeletal structure of the car. This is the monocoque frame that is used in the Tata Nexon. Let's take a short drive down the frontal part of the chassis to understand the design and its functions. First thing first, the engineers create theoretical models for references. Take a look at this crash pulse graph. The strength of material, what's simply called SOM, and the vibrations are studied in order to calculate the forces acting upon the structure in a given scenario. In this case, it is the frame of the Tata Nexon colliding with an unmovable barrier, say something like a wall. Engineers consider materials, weight, speed, and the other factors to calculate and come up with a theoretical model. They take the data from previously tested designs and try to improve on it. Engineers design the bumper, crush boxes, and longitudinal rails in such a way that the frontal frame should deform and absorb most of the energy when colliding with the barrier. Crush boxes must deform in layers like this in order to achieve the goal of protecting the occupants of the car. So they consist of multiple crumble zones. Crumble zones are the spots where the deformation of the frontal chassis occurs. They are designed to allow deformation to take place in a way that ensures other components of the frame stay less deformed. Crumble zones reduce the unpredictability of the damage done to the frame by an external force. It also helps in delaying the energy absorption process, thereby reducing the risk occupants face in the crash. The energy then gets transferred to the longitudinal rails which are connected to the platform. These rails are also crumbled in order to absorb energy, otherwise it will enter into the occupant's cabin causing fatal damage. But the frame's design should be such that it absorbs most of the force, preventing the occupants from taking a fatal hit. The Tata Nexon uses rectangular crush boxes and longitudinal rails and an HSS or high strength steel frame. Once the design has been finalized, the material are decided upon. Then the mesh models of the design are created. Meshing means breaking down the geometry of the design into small blocks. This ensures the analysis report is as close to accurate as possible. In a 3D model, the mesh models will act as a 3D blocks like a cubes, pyramids that are used to build the structure as much like an Lego blocks. The software calculates the forces for each of these simple blocks and comes up with a nearly accurate analysis of the entire design. After the meshing is done, they simulate the crash in the software. The software performs different tests on the model and provides the data of the test. The data then goes into the validation process whereby the simulation data is compared to the theoretical data. If the data matches the desired results derived from the theoretical models, then the engineers move to the next step of the process of prototyping, a physical model for further testing. If not, the engineers find the problems in the existing virtual prototype model and make changes. Once the changes are made, they are put through the simulation. This iterative process ensures that the prototype or the production model that is sent for physical testing is strong enough and it is first time right. In the other cars that were produced earlier, Tata mostly used the body on the frame chassis because it is cheaper and faster to manufacture. Let's take a look at this SUV chassis. It is a ladder frame chassis as it has two longitudinal rails throughout the body. They are very heavy because they have to bear the weight of the body. Due to the lack of crumble zones, the frame does not deform, so the energy doesn't get absorbed at the initial point of the collision. Since the body is attached to the chassis separately, there are high chances of the body getting detached from the frame, causing grave harm to the occupants. The intrusion in the occupant's cabin, in this case, is high, raising the danger level. For example, in the case of this SUV, hitting the barrier at the speed of 64 kmph, you can see the driver's cabin deforming and reducing the driver's space and crushing the people inside. Poorly designed crumble zones or the absence of them allows the rails to bend in any direction. Whereas in the Nexon design, we can see the energy being absorbed by the frame. The bumper is distributing the energy to the crush boxes. The crush boxes absorb the majority of the energy by deforming, and the remaining energy travels through the rails to the floor pan or the platform. And the apron distributes the energy to the pillar, which further distributes the energy to the upper frame of the design. Incorporating FEA in the design stage of a product is vital, as it ensures that the product is safe and reliable. Moreover, companies don't have to spend a lot of money on physical testing of the products. All of it can be simulated virtually and adjusted so we can take the car out for a smooth and safe drive.